computational approach to predict unsaturated soil phases. The project is presented by Hiram ARROYO, José Marcelino Gutiérrez-Villalobos, and Xavier CHAVEZ-CARDENAS. The three of us are professors from the Universidad de Guanajuato in Guanajuato, Mexico. So the unsaturated soil phases, this project aims to present a model to predict unsaturated fractions in a porous medium such as a soil. This because of the result of the process of natural humidity changes that occur in environments where both the temperature and relative humidity of the environment are constantly changing. Because of this, these processes are important and need to be studied to predict the resistance and permeability that the porous medium may have under various scenarios. In this regard, the prediction of the unsaturated soil fractions under a computational model that allows us to predict the volumes of the unsaturated fractions is of paramount importance. As an introduction, we are presenting the methodology to develop the computational approach to establish an algorithm for this. Soils are the most, as an introduction, we'll say that soils are the most common construction material in civil engineering practice. Its mechanical and hydraulic behavior, unlike conventional materials such as steel or concrete, are far from being well understood. For example, sand materials, which are among the most homogeneous materials, classified according to the Unified Soil Classification Systems as SP, like as poorly graded sands, are homogeneous material which may have particularly homogeneous size of solid grains. However, even though these are uniform materials, in civil practice, they still present lots of heterogeneity in terms of their mechanical and hydraulic behavior. For example, sometimes the flow of water in soils leads to variations in soil water content. These factors are the main issue that affect the flow of water, inducing permeability changes and mechanical variations such as volume strains. In order to develop a computational algorithm for this, we're going to present a model that allows us to describe the internal microstructure of a soil through a very simple process. This is a matter, of course, of utmost importance as it leads to a description of the density of the soil sample, so it needs to be a feasible and represent a feasible way to describe the microstructure of the soil, as it has various important implications for various percolation processes, such as the air entry value. For example, solid particles of the same size are most likely to gather frequently, consequently producing pores of the same size around them. So as you can see in the figure, the structural geometry distribution of the pore structure is arranged in terms of sides, bonds, and sides and bonds. And this will be carried out in a square grid of m rows times m columns, where the intersection of each row and column there is a side, and where the sides are joined by bonds, as shown in the figure. It is important to determine that the number of sides and bonds that the numerical model will have will be determined by the frequency of each of them in the porous matrix. This frequency is commonly obtained from the pore size distribution, which is evaluated from the mercury intrusion porosimetry test. The frequency distribution can be expressed considering the equation number 1, where f is the frequency and n is the number of sites contained within the porous matrix. Therefore, the number of required sites for a certain size will thus be the element described in equation number 2. It is important to say that before placing any site in a random site, it is scanned in order to see if there is already any bond connecting to it. And if it is any bond connected to it, we will see and express if it can be connected. Well, the first scenario would be that the spot is without any bond and interconnections. Then a completely randomly site is chosen from distribution and placed on the empty spot. In order to do this, it will be placed only if it is greater than the given condition to avoid for the intersection of B1 and B2. This is because if it is too small, it will produce an overlap between the two bonds. So the condition to place the bond is expressed by the equation of where the radius of the smallest site to be placed is the square root of the square sum of the radius of the bonds that are intersecting to the connection. At the first stages, of course, the grid is completely empty, and it is very easy to find a place to place the sites where they are to be placed. As the process progresses, it is very hard. It goes harder and harder to find a site and the bond to connect and to comply with the conditions that have been previously expressed. The described process at the early stages is really easy. However, as it progresses, it's somehow difficult to find. However, the best site and the best bond to comply to be placed in this spot are needed to be found nonetheless. Once the grid is completely covered with sites and bonds, it is important to try to simulate a process that allows us to retrieve important hydromechanical properties of the material. One of these is the desaturation process, which can be simulated with the grid matrix. Using Laplace's rule of capillarity is the one that it is shown in the slide. This equation establishes the relationship between the suction level reached during drying and the pore size that must be dried, where T sub S is the tensile the coefficient of tensile stress between air and water phases. Phi is the water solid, the fluid solid contact angle. S is the suction, and with this equation we can allow imposing suction to the constructed porous matrix, correlating it with the pore size that must be dried. Concerning this, we have overlapped the predictions of well-established process, well-known probabilistic model expressed by Eduardo Rojas in the Universidad Autónoma de Querétaro in Mexico, where it can be seen in the figure placed in the slide that the model, which is actually the red solid line contained there, correctly agrees the results of the computational model with the same model parameters. These model parameters are contained in table 1, which are actually the model parameters of a standard deviation test in the semi-logarithmic scale. Which are these results? These results are expressed in terms of the relative volume of the unsaturated phases, unsaturated units, which are actually the volume of the solids, of the voids that are surrounded by either dry or either wet pores. This is a very important property because it is closely linked to a lot of hydromechanical properties of a soil along its drying process, and it can be seen, as I have already said, that the red line gathers very closely to the computational model. Here, it is important to look around this completely agreement between the computational model, which actually confirms that the model that we have presented herein has a very good future in terms of its usability. As conclusions, we are going to state that the research work has presented a computational model generated through a simple algorithm that allows us to simulate important characteristics of the drying process in a porous medium, as it considers the interconnections between linear bond type elements and elements that store the water within the soil. As the conditions to dry need to be met in order for the material to dry, and comparing it, the model presented herein has been contrasted with another model, a well-established model, and they both coincide. So finally, the conditions are a function of the size of the pores that surround it, as well as for the levels of suction achieved. We thank you for your attention.